All right, so we're talking about random variables and how they could be discrete or continuous, and how if they're discrete, they could be finite or infinite. So let's keep going with that. So example of a discrete random variable, let's consider rolling a six-sided die. The random variable z represents the outcome of rolling the die, right? So z, the variable, represents the outcome of rolling the die. Z can take on any one of six possible values, 1, 2, 3, 4, 5, or 6. So here's a question for you. Is z going to be discrete or continuous? Answer that question. Okay, you got it? It's going to be discrete, because discrete is like there's no fractions there. And the random variable is going to be 1, 2, 3, 4, 5, or 6. And now I have another question for you. Is this finite or is it infinite? And it's going to be finite, because finite means it has a limit. It's finite. It has a limit to what it could be. And that limit is 1, 2, 3, 4, 5, or 6. If this was like the number of people coming to see the World Trade, I don't know, does that building exist anymore? I don't think it does. Number of people coming to see the Golden Gate Bridge, that could be infinite, right? Like it could just keep going and going and going. There could be no end to it. So this is a discrete random variable that is finite. If we roll the die and it shows a 4, then we say z is equal to 4. Connecting random variables to coding schemes. Just as a random variable assigns a number to the outcome of an experiment, coding schemes assign binary code to a character or a piece of information. So that's how that works. And we've kind of been over this, so I'm not going to go over that. But you can pause the video and you can read through that just to kind of connect those dots there. The next thing is we'll just look at a couple of examples here in the PowerPoint presentation. Here's a discrete random variable with a finite number of values. An accountant taking a CPA exam. The exam has 4 parts. Let the variable x equal the number of parts of the CPA exam passed. X may assume the finite number of values 0, 1, 2, 3, or 4. Right? So that's discrete. It's finite. It's a variable. The variable is representing the number of parts of the CPA exam that was passed. Right? So the number of parts of the CPA exam that was passed is what the variable represents. Here we have another discrete random variable that's infinite. Cars arriving at a toll booth. Let x equal the number of cars arriving in one day. Right? So our variable represents the number of cars arriving one day, where x can take on the value 0, 1, 2, and then just on and on and on. So that's infinite. It could just keep going. We don't know where that ends. But it's still discrete, because we're not going to get, a fraction of a car rolling through. But that's funny to think about. We can count the customers arriving, but there's no finite upper limit on the number that might arrive. And so here we have a couple of more. And a random experiment of flipping a coin. The variable is the face of coin showing, right? And 1 of heads and 0 of tails. That's the random variable. And here we roll a die, number of dots. And so we'll talk. Well, I guess we'll ask this as we go. Is it discrete or continuous? Is it finite or infinite? This is discrete, and it is also finite. Roll a die, number of dots showing on top of a die. So do you get a 1, 2, 3, 4, 5, or 6? This is finite, and it's also discrete. Contact 5 customers, and the variable is the number of customers who place an order, and the possible values for the variable are that. So that's again discrete and finite. Operate a healthcare clinic for one day. The variable is number of patients who arrive. This is going to be discrete and infinite, right? That's why we have those. And offer a customer the choice of 2 products. And the random variable is the product chosen by the customer. And so here, 0 if none, 1 if choose product A, 2 if choose product B. So we have, here discrete, 0, 1, or 2. And it's also finite. Those are the choices, 0, 1, or 2. And we're learning about variables so that eventually, down here at slide 17, we'll be able to see functions. And so a function, if this is our random variable, and this is like the number of cars sold each day, so this is going to be a discrete random variable that's finite. It could actually be infinite, but we're only measuring it through 5, because you could just sell more and more cars every day, but practically the probability of that occurring is low. We could create a probability function, and we could say, hey, 0 cars being sold, the probability of that is 0.18. 1 car being sold, the probability of that is 0.39. 2 cars being sold, the probability of that is 0.24. 3 cars being sold, the probability of that is 0.14, so on and so forth. Now, how is this different than just like some frequency distribution or something similar to that? Is that we have a function here, and this is function notation, and this is the kind of notation you'll see in computer science. And when you have a function, this x is being passed into this function f, and this function can represent, some sort of function, meaning it's some sort of an operation that produces some sort of a result. And when we pass in the value, whatever the variable is, right? So we pass in 2, the function's going to spit out 0.24 as our probability. If we pass in 4, the function will spit out and pass in, meaning x is 4. So when this is 4 cars are being sold, the probability of that is 0.04. And again, this might just seem like, intellectual gymnastics and overly complicating things. But what it is it's a framework for starting to think about doing statistical problems. And hopefully, and I didn't get my PhD in statistics, but hopefully what that means is that this framework will allow us to think about more complex problems and to simplify them, or at least allow us to more accurately get the correct result, because we have a framework for sort of thinking about that. But that's the reason we're learning about random variables and having a variable represent an outcome of an experiment, so that we could create some notation where we're representing, different outcomes, and we have some function where we could pass in one of the outcomes, and it'll pop out the probability for us of something occurring. But it's just a framework in statistics for thinking about probabilities and stuff like that, for thinking about data and different stuff that can occur. So that's random variables, and we're going to learn some more stuff coming up. And the next one, we're going to learn about discrete probability distributions. See you in the next video.